overall, I was not unhappy with the exam. If you are particularly unhappy with your exam, please first read the key, compare your answers, check it all out, and then come talk to me. Happy to go back through that with you at any point in time. I want to go back to looking permutations at groups in general, and it turns out one of the things I will be able to show is that almost every group, I actually do think it is every group, can be represented as a group of permutations. And if that's the case, it really means if we understand the way in which permutations behave, we get it all. But I need to talk more about the things that are preserved. So let's go back to our property. So we have two groups, G and G prime. We have a function from one to the other. We had an isomorphism. What made an isomorphism? What made a function from one group to another an isomorphism?
If there exists a bijective homomorphism.
Okay, bijective means?
Two.
Say again?
Bijective two.
Bi means two. What's the jective part?
They share the same set or something.
There's a lot more specific behavior there. What's a bijection?
It's one, on two.
One, and on two. And there was another word you used. What's that?
Homomorphism. I'll be 100% honest. I've never heard of that, so I just read it.
So you got to write that definition you understand. That was a property we had, right? Ben?
Is that the one and on two function that maps one set to itself?
If it goes from the set to itself, that's an automorphism. But there's still one other property, that homomorphism property behavior. It has to be preserved somehow. There's some other thing that gets maintained. What's a homomorphism? That specific word we haven't used yet on its own. We used it as the homomorphism property. What's the homomorphism property? If you go to the index of your textbook, you can look up the word homomorphism property.
So the function of A star B equals the function of A star the function of B.
Aha! Rather than use star, I'll use my multiplication notation. So phi of AB is phi of A, phi of B. Because I don't know whether or not these groups are abelian or not, so I'm not going to use the additive notation. If this is true, then for all A and B in G, then phi is a homomorphism. So this definition strips away the one-to-one and onto part and allows me to say, Noah, exactly as you did, that an isomorphism is a homomorphism that's also bijective, one-to-one and onto. But I need that definition separate. So any map that does this, even if it's not one-to-one, even if it's not onto, still satisfies this homomorphism property. We're going to call it a homomorphism. Now this sounds really dumb, but here's an example that I think you should get. Let's go from the reals to the complex numbers. All right, somebody tell me what this thing does. I've seen these numbers before.
Did we see that in DiffyQ?
No, we saw it right here in this course,
Oh,
but I also saw it in DiffyQ. But I actually saw it here in this course. I want to use the version we saw in this course. What is that e to this thing?
We need the polar coordinates.
Aha! That's our polar coordinate setup for complex numbers. So in this case, that would be cosine of 2 pi t plus I sine 2 pi t. And in the complex plane, that's a number on the circle of radius 1. That's part of my unit circle. Sure it is. Somebody pick a t value. 4. If I put in 4, what do I get? E to the 8 pi I. Cosine of 8 pi. 1. Sine of 8 pi. It's a multiple of pi, 0. That's right here. That's the point, 8 pi I, 1, 0. As a complex number, just 1. Pick another number. Put in 5. What do you get? 10 pi I. E to the 10 pi I. Cosine of 10 pi? Sine of 10 pi. Same point. As a matter of fact, every integer maps to that spot. This function is absolutely 100% not one-to-one. If you picked any integer, 0, you'd get cosine 0 plus sine I sine 0. That's 1, 0. You pick -3, you get cosine of -6 pi, 1. And sine of -6 pi, that's 0. Same damn point. It's guaranteed not to be onto. Why? I don't get all the values in a circle? Well, let's pick another point on the unit circle. Up here, right? That point's on the unit circle. What angle is that? Well, according to the question.
Prior to.
So if I put in 1/4, I'll get that angle, won't I? Aha. It turns out that I do get every point on the circle just by varying this number to be something not an integer, right? This is going from R. I don't have to pick integers. I can pick any number I want. If I pick 0.537, I don't know what 2 pi times that is, but that'll be somewhere over here on the circle, right? I pick 0.537. That'll actually be down here. Because that number will be times 2 pi. It'll be bigger than pi. It'll be down here somewhere in the third quadrant. I pick negative 13.6. Multiply by 2 pi, you'll get an angle. Go to that angle, you'll get a point on the circle. But Neil, what points won't I get? Ever. Help out somebody. I'll never get a point that's not on the circle. No matter what t you put in, this returns a complex number whose distance from the origin is 1. I'm never going to get the origin itself. I'm never going to get the point out here at 2, 3. I'm never going to get the point down here at -5, +5, -7. I'm never going to get a point in the complex plane other than the points on this circle. So I'm missing a whole lot of the complex plane. This is not onto. There's no C in R with phi of C even just equal to 0. But okay, screwed up ever so slightly. Back up there where I wrote R and C, I need to give these as groups, right? If I'm using R, what operation am I using? If I tried to use multiplication, I'd have a problem because 0 is in there, right? So let me do this under addition. But I think I do want to do this under multiplication. There. Now I'm not worried about 0 anymore. Phi of A is e to the 2 pi I A. Phi of B is e to the 2 pi I B. Over here I'm adding, over here I'm multiplying. So I want to look at phi of A plus B. What is that?
Just need those two added together.
Oh, careful. This now goes where this is. But when you add powers, what do you do with the bases? Aha! This is a homomorphism. It satisfies the homomorphism property, but it doesn't become an isomorphism. It isn't one-to-one. It isn't onto. But it does satisfy that special property. So this is a way of saying that the actions within these two sets are related to one another. Even if I didn't have an isomorphism, even if the behavior is not exactly the same, the action is preserved. Some definitions we've used before. If I have any function from x to y, and a is a subset of x and b is a subset of y, I'm going to think of taking everything in x and running it through phi. We're going to call that the image of x. Now, really, it could be the image of a, phi of square bracket a. The set of all phi of little a, such that a is in a, image of a. Instead of just the image of a single point, we can talk about the image of a whole set. And that is a subset of y. As we move from our set x over. But what if we start over there and work our way back? Off the bottom of the page, you can't see it. Pardon me for a second, there's a bunch of cables tangled up back here. It's causing me to lose room. There we go. So I look at this set B, and I look at all the things that hit it from X. This is called the pre-image of B, or the inverse image. The reason I'm loath to use the word inverse here is that inverses only apply to one-to-one and onto functions, or one-to-one functions. I don't want to do that all the time, so I tend to use the phrase pre-image more often. Ian, you look like you were going to ask a question.
Not anymore. It was just I was confused by what something was written and I figured it out.
Okay. Notice that the pre-image is back in X. Why do I want these terms? Because I want to think about what goes on in groups. I'm going to apply this idea to our group homomorphism. If I have a homomorphism, then the image of the identity must be the identity. The inverse of an image. The inverse of an image must be the image of the inverse.
You said it all the time.
The inverse of an image must be the image of an inverse. The image of a subgroup must also be a subgroup. And the pre-image of a subgroup must also be a subgroup. Isomorphism told me everything was exactly the same. Homomorphism tells me they might not be exactly the same, but the structures within these items are similar. That's why we use homomorphism rather than isomorphism. Iso means exactly the same. Homo means similar to. Questions? How about, because this was what, yes, Jim?
What is the 4 prime?
If K prime is a subgroup over in G prime, in other words, it's in the codomain, the range set, then when I move it back and look at the pre-image, that's also a group. So the third one says the image of a subgroup is a subgroup. The fourth one says the pre-image of a subgroup is a subgroup. Which means what we did is we preserved the identity. The homomorphism must map the identity to the identity. It preserves inverses. It must map the inverse to the inverse. And it preserves subgroup structures, both moving forwards and backwards. You've got a subgroup in the left, you have to have a corresponding subgroup in the right. You've got a subgroup in the right, you have to have a corresponding subgroup in the left. They have to match up structurally. I will say that these are in order for a reason. Because in order to prove something is a subgroup, you have to prove it has an identity and has inverses. So I need 1 and 2 to prove 3 and 4. But that means I better be able to prove 1 and 2. And the advantage is they both follow from the only thing I need for a homomorphism, which is the property we started with. So off the top of your head, what's that property again?
Which one?
The homomorphism property. The only thing I need for a homomorphism.
It was given A and B have phi of.
Go look, people. I know I said off the top of your head, I was being facetious.
Phi of AB is the same as phi of A times phi of B.
Right. Phi of AB equals phi of A, phi of B. So, if phi is the identity, if E is the identity in G, let's prove number 1. Suppose E is the identity in G. What does that mean?
Does that mean?
Yeah, what does it mean for E to be an identity?
That means that E times, are we using times here? Well, yeah, so E times anything is itself.
Okay. For any element in my group, EG equals G. Okay, wait a minute. Let's apply phi. That means that phi of G is the same as phi of EG. Apply your homomorphism property. What's phi of EG?
E times E, phi times G.
Except that's phi of, not phi times, but yes.
Yeah.
But wait a minute, that says that phi of G is equal to this thing times phi of G. Doesn't that make this an identity? Because if you multiply it by something in G prime, and you get that same thing back, that makes this an identity. By the way, I only did my version of it with E on the left. I should do it with E on the right as well, but it's the same damn calculation. Once you have an identity, you have inverses. Once you have inverses and closure, you have subgroups. The rest of the proof is on page 78 in the text, I believe. Questions? Let's go back and look at our example. Our example was the map that took the additive real numbers to the complex plane. And it took it to the unit circle, right? Didn't we have a name for that set? What did we call that set? Back in like chapter 012.
Is that the roots of unity?
Almost. The roots of unity was a finite set. The roots of unity were all the numbers that were like e to the 2 pi I over n for some n. But this itself was the whole circle. We gave it a name as the unit circle. We called it the group U. Okay, wait a minute. We had it as a group, right? So that means the image of R is the unit circle, and that we know is a subgroup of the complex numbers under multiplication. And that's what 3 said. 3 said, hey, you've got the image of a set, it's got to be a group. This is a group. I take it over here, it's still got to be a group. But you said roots of unity as well, right, Ian? The roots of unity, we used U4, right? If I remember correctly, U4 was the set 1i, -1, -i. That is also a subgroup of the complex numbers under multiplication. It's not just any subgroup, it's a cyclic subgroup. It's generated by I. That's over here in the complex plane. What's the pre-image of that? What are the numbers that map onto this set? Well, what I know from up here is that that must be a subgroup of the real numbers. It's a cyclic subgroup of the real numbers. And if I remember correctly, we determined what every subgroup of the real numbers looked like. They were generated by some number. So I can figure out what the subgroup of the real numbers is that always hits these 4 points on the circle over and over and over and over again. Wait a second. 1. T is 0. I get the point 1, don't I? The identity has to map to the identity. The identity in the integers adding is 0. The identity in multiplication is 1. 0 has to line up with 1. What angle puts me here? Okay, pi over 2, is that what number t is going to get me pi over 2? 1/2, right? No, 1/4.
Yeah.
1/4. And then -1. That's going to be the angle pi. What number is going to give me the angle pi? Or +1/2, right? If I go this way or if I go this way. And then here, what angle gets me to -I? -1/4 or +3/4. Wait a minute. Wait a minute. Wait a minute. 0, 1/4, 1/2, 3/4, -1/4, -1/2. This is the cyclic subgroup generated by 1/4 in the real numbers. The pre-image of a group must be a group. Son. And that means the properties of those subgroups are the same. They're both cyclic. Hot damn. Ooh, wait a second. This went to the identity, right? Phi of 0 was 1. Let's consider the preimage of the identity in G prime. I'm going to give this set a name. Those of you who have taken linear, are taking linear, will hear this name again. We're going to call it the kernel of phi. We're going to write that as KER phi. And by definition, this is the set of elements in G so that phi of G is equal to E prime. In our example, that's the entire set of integers. 0 gets mapped to 1, 1 gets mapped to 1, 2 gets mapped to 1, because that's a 2 pi, and a 4 pi, and a 6 pi, and a minus 2 pi, and a minus 4 pi, and minus, all of the integers hit the point 1, 0 on our unit circle. In our example, the kernel of phi is equal to z. What's one element you can always guarantee is in the kernel of any homomorphism? Fill in the blank.
Did you say 0?
I don't know that 0 is part of my group, do I? Because this says for any homomorphism. I don't know what G is. I don't know what G prime is. But I want to use the identity, so I can generalize this. And I can say that the identity from G. Because that was the first result in our theorem, that the image of the identity, E, must be E prime in the other group. In our example here, the preimage, the kernel, has infinitely many elements in it. But that's not always the case. Sometimes the kernel is finite. Sometimes the kernel is infinite. It depends on the particular map we are looking at. Knowing things about the kernel of a homomorphism tells me a lot. More on that in a little bit. Questions? With the exception of applying this to groups, all of these ideas showed up in chapter 2 in discrete, where we did one-to-one and onto functions. Because we talked about what maps to where, whether it mapped more than once or not more than once, in many different ways. For any n, a subgroup of Sn is called a group of permutations. Well, that makes sense. Sn is a permutation group on n letters, numbers, elements. So I'm taking a subgroup of that. All right. Here is an amazing claim. I don't care what group you are using. Every group under the sun can be turned into a group of permutations. At this point, people usually tell me, bullshit. How the hell do we do that? I am going to start with a very simple example. Way back, I think in chapter 2, we showed that there was one and only one group of order 3. We did this by drawing a table. I'd like to recreate that table right now. So let's start with a group table. Here is a group of order 3. I would like you to fill in this table. There is only one way to actually do this. What do I get?
EAB.
Across the first row?
Yeah, across the first row, and then going down as well, AB. Would it go B?
Because if I were to put an E here, each thing can only show up once in each row and column. If I put E there, I'd have B, and that would be a conflict. So there's got to be an E here, and that means there's got to be an A here. Rows or columns? Columns. So what I need you to do is I need you to write the leftmost column. And then each individual column as a permutation. Before you look at me like I've lost my mind, let's take the first column and the column for E. This first column, that's this one under the star. The right column in my permutation is the column for E. Now, normally we would write these as rows. And I'm okay with that. Now, do the middle column, the A column, here. But that's only going to be the right column. So A looks like this. And B looks like this. Hey, wait a minute. Let me think about these as permutations for a second. So instead of using E, A, and B, I'm going to use 0, 1, and 2. When we think of permutations, we usually think of numbers, right? Or you could use 1, 2, 3. Doesn't matter. Let's use 1, 2, 3. This permutation is the permutation 1, 2, 3, 1, 2, 3. Wait. That's the identity permutation, isn't it? Takes everything to itself. This is the permutation 1, 2, 3, 2, 3, 1. 1 goes to 2, 2 goes to 3, 3 goes to 1. Wait a minute, in cycles, that's 1, 2, 3. This one goes like this. What's the cycle notation for that? 1, 3, 2. I've just found a way to make that table a subgroup of S3. How do I know that? Because we did these multiplications. 1, 2, 3 times 1, 2, 3 is 1, 3, 2. 1, 3, 2 times 1, 3, 2 is 1, 2, 3. 1, 2, 3 times 1, 3, 2 is the identity. Those are inverses of each other. These three permutations behave exactly the same way that E and A and B behave up there in that chart. Now I've written the permutations. Created a group of permutations that exactly mimic my chart. Now, Jalen, you picked columns. Any particular reason why? No, exactly. It's coin flip. You could just as easily do this with rows. This group is abelian because that table up there is symmetric, which means when you do the rows, you get exactly the same picture. You get exactly the same permutations. That's called the row representation or the column representation of your table. All right. This particular setup came from Z3. Because that's what that table is up there. That's a group of order 3. It's abelian. It's Z3. Damn it. That's 0, 1, and 2. And then I just turned it to permutations, which is in S3. But no matter what group I take, whether it's abelian or not, I can do this same thing. Here, on page 80, is a table. This is the table for D3. What the is D3? What? And dihedral meant these were the symmetries of a three-sided shape. So this is a triangle. This is the triangle group. You pick up the triangle, you turn it, twist it, drop it back down into the hole. Figure out where the corners went. You have the identity, a rotation by 120 degrees, two rotations by 120 degrees, a rotation by 240 degrees, a mirror, and then a mirror with a rotation or a mirror with 2 rotations. This group has 6 things in it. And here is the table. Notice when I do row times column, I'm doing multiplication on the left. So this entry is P times mu. But P times mu isn't one of the things, so I would have to go through the Cayley digraph to figure out which one I landed on, right? We did this Cayley digraph. Doesn't that look familiar? Triangle within the triangle. I could do a row representation or a column representation from this table. Pick a row. I don't care which row. Pick a row. Okay. I'm going to write that down along with the top row. So, from page 80, no, it's just 3. The second row was the row for the rotation. So there's the top row where I listed everything in order, and now I get this. Now that looks like hell, doesn't it? But that's a permutation. A permutation in S6. If I number these 1, 2, 3, 4, 5, 6, 1 goes to 2, 2 goes to 3, 3 goes to 1, 4 goes to 6, 5 goes to 4, 6 goes to 5. Which, if you notice, really makes this 1 goes to 2, 2 goes to 3, 3 goes back to 1, 4 goes to 6, 6 goes to 5, 5 goes back to 4. I know which permutation in S6 this is. Let me look at the column version. Here's my table. Look at the column that goes with P. P, P squared I, MP, MP squared M. MP, it's different, isn't it? It's different. D3 is not abelian. The row version and the column version are different. Okay, I should formalize this. Definition. G, a group. Order of G, finite. Phi from G to S order of G. D3 had 6 elements in it. We got permutations that live in S6. The first group we did had 3 elements in it. We got permutations that live in S3. If I have 100 elements, I get permutations in S100. Given by phi of G equals lambda sub x. Lambda sub x of a group element puts x on the left of G is the left regular representation of G. Row version. This is the way we created the permutations we were doing. We defined each image by what happened when I did that thing on the left, and that was what we did with the row. And this is a permutation. It's a function from G to itself. By the way, there is an exact same definition called the right regular representation. What's the difference? That's the column version. And it's GX instead of XG. The X is on the right instead of on the left. I think the textbook uses tau, but you could also use the inverses. A familiar name comes to the forefront. In order for me to prove this is an isomorphism, first I have to show it's a homomorphism, then I have to show it's one-to-one onto, right? But this function right here, by its very definition, is one-to-one onto into the subgroup of permutations that we've created. And got to satisfy the homomorphism property because it's doing our group multiplication. The proof's in the textbook. I don't want to rewrite it for you. So I think you should read this one. By the way, it is absolutely important to note that the group we create here is not necessarily the smallest group that would work. D3 itself turns out to be isomorphic to S3. But we built it in S6. As a matter of fact, I can even show that D3 is isomorphic to some subgroup of S5. So I don't necessarily get the smallest possible subgroup. As a matter of fact, this is usually a very cumbersome, very large subgroup, but it's a way to show that every single group is a group of permutations. That means really what I want to know about is groups of permutations. As much as I like doing Zn, and working in the integers, or even working in complex numbers, which I know you all adore so much, it turns out working in groups of permutations is the deeper, more structurally clear way to work in groups. It does change the way we think a lot, though. A lot. Oh, and by the way, this even applies to groups that are infinite, but we can't use this version because this version was defined using the table, right? I could take this away and everything in this definition still holds. But figuring out what group element is what is a lot harder. And that becomes part of something that we do in a second semester linear class, which we don't have here. Questions? I want to introduce you to my favorite pieces of groups of permutations. What is a transposition?
Suppose you had a triangle, would that be like shifting it just to the right? You know, on like on the plane?
Unfortunately, no. I'm thinking strictly in terms of a permutation idea, but what you're thinking about is a translation geometrically. What's a transposition as a type of permutation?
Is that when it flips the order?
Yes, but there's more. It only flips two things. It switches A and B and doesn't touch anything else. And then if you do it twice, it switches them back. Now here's something interesting. If I have a cycle of length n, I can rewrite it as a bunch of transpositions in two different ways. I can do it by flip-flopping each one in order. A1, A2, A2, A3, A3, A4, A4, A5, all the way up to AN minus 1. Or A1, AN, A1, AN minus 1, A1, AN minus 2, dot, 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 A1, A3, A1, A2. In this version, the first entry in all of the transpositions is A1. In this one, the order is preserved from the way we see it in the cycle. So something like 1, 3, 2, 4, 5. If I use the top version, I would write 1, 3, 3, 2, 2, 4, 4, 5. If I use the bottom version, I would write 1, 5, 1, 4, 1, 2, 1, 3. You should actually check that these work out to be the same thing. I guarantee you they will. but you should check. Please note, if I can break any cycle down into transpositions, it means I can break any permutation down into transpositions. You did this on the exam. Here's a write it as a product of cycles, didn't you? You wrote it as a product of disjoint cycles. Now each of those cycles can be written as a set of transpositions. So this 25316 becomes 232516 or 255316, depending on which version of the transposition breakdown I use. No matter how big your permutation is, I can turn it into transpositions. Hey, even the identity transposition. Wait a minute, we were calling that I in the D3 book, right? The table. Well, I could just write that as 1, 2, 1, 2. Switch them and switch them back, and you're done. Everything went back to where it started. What do you notice that is fundamentally different between this breakdown of this cycle, permutation, and the breakdown of this permutation, and the breakdown of this permutation? Something fundamentally different between the three of them. The top one had 4 transpositions in it. The bottom one has 2. The middle one has 3. But those are not unique, because if I took this permutation, I could multiply by the identity if I wanted to, right? And it wouldn't change anything. Then we have 5 transpositions instead of 3. No matter what I do, I'm not going to change the number from even to odd or from odd to even. I've written it as a theorem. That means I should be able to prove it. People, proving this sucks. The proof in the textbook counts cycles. I hate this proof. There is a proof by determinants that is 2 sentences long. For any transposition, take the identity matrix and switch the rows indicated by your transposition. So this permutation right here, row 2 goes to row 5 goes to row 3, row 1 goes to row 6. What's the determinant of the identity matrix? 1. Switch rows, what happens to your determinant?
By -1 to the I'll make a revenue switch.
I did 3 switches here. My determinant is now -1. I did 4 switches here. The determinant is still 1. I did 2 switches here. The determinant is still 1. You can't have something whose determinant is 1 and -1 at the same time, can you? You either get an even number of switches or an odd number of switches. Period. End of story. The proof in linear is literally 2 sentences. The proof in the textbook, which counts cycles, is about this long. I hate it. Don't read it. So I'm going to call my permutations even or odd, depending on how many transpositions they break into. Please notice, this cycle is even. There are 5 numbers in here, but it breaks into 4 transpositions. This is odd. There are 5 numbers here, but it breaks into 3 transpositions. So it doesn't tell me how many numbers are involved, it tells me how many transpositions are involved. This is even. In one way, you could say it has no transpositions. In another way, you could say it has any even number of transpositions. They just switch and switch back. The number of even permutations is exactly the same as the number of odd permutations. It means Sn gets split exactly in half. The even group and the odd group. But the identity lives in the even group, right? That means the even group is the one that could be a subgroup. The odd group isn't. How do I know it's closed? If I take 2 permutations and I multiply them together, I add the number of transpositions. Well, even plus even is still even. Even if some of them cancel out, they cancel out in pairs. How do I know it contains inverses? You just write the transpositions again, and you've got the inverses. Closed contains the identity. 1, 2, 1, 2 is even. And it contains all the inverses. It must be a subgroup. As a matter of fact, it is an important subgroup. We're going to call it the alternating group. On n letters or symbols. And remember, I was talking about whether you map them to being odd or even as being 1 or -1 by the determinant. Here's a map. We're going to call it SGN of sigma. The sign of a permutation is 1 if sigma is even, -1 if sigma is odd. This is a homomorphism where this group is under multiplication. And the kernel of this particular homomorphism is exactly the alternating group. By the way, we will show in one of the very last chapters that A5 is a critically important group to solving polynomials. If you came in late, I still have your exam. Regardless of whether you came in late or not, I forgot to collect homework at the beginning of class, so please give that to me on your way out. And I'll give you your exam as well.
Yeah.